Okay, this is example 4 or 5. This one is going to be of a cantilevered beam. This is how the problem was faxed to you, not faxed, emailed to you, sorry. It's a cantilevered beam with 2 loads on it, 85 pounds and 75 pounds at the tip. So basically I'm going to redraw it on this larger piece of paper. Also, by the way, all these that I'm posting on videos, it's not enough to watch these videos. You better do this problem like I'm doing and understand it and be able to do it from scratch. If you think you're going to be able to watch the video and then do it on an exam, remember this final exam you're going to take, you'll have to do it in person. So on the test 4, there'll be a test 4. If the conditions don't change with this quarantine, you'll get that to do at home. But anyway, my advice to you is get these. You're going to get them in this format. Put them on a big piece of paper, draw them out, do them meticulously like I'm doing. And then once you find out you can do that, then you'll understand it. And studying, you won't even have to study once you know how to do this. Anyway, back to this cantilever problem. On this one, this is the reactions. I'm not going to go through it, but basically you got to be able to put this in static equilibrium. You can pause the video, and that's how we did that. We got a moment of 1580 going there and a reaction of 160 pounds going up, and that puts this cantilevered beam in static equilibrium. Really, the only caveat to a cantilevered problem is one thing, is that the moment value does not start at 0. The moment value, instead of starting here, is going to start at that moment value. It'll be negative, because we said this is positive, right? That's the positive rotation. This negative value is going to start down here. Anyway, let me show you how the shear goes first. Same as the other problems. 160 pounds, I'm going to go here. I'm going to go up to 160 right there, right? I'm going to go constant across in between concentrated loads. 160 minus 85 gets me down to 75, right? Then constant again. And then 75 closes me up, right? So I have a very simple shear diagram for that, right? Now the moment's a little harder. This is where I'll use that again. So point A, we say that VA is equal to 160 pounds. MA is equal to not 0 as it was before, negative 1580 pound-inches, so not 0. And I'm going to put a point at negative 1580. Okay, that's where I'm going to start. At point B, we have VB is equal to my old shear value, which is VA minus 85 is equal to 160 minus 85 is equal to 75. That's that value right there. MB is equal to the old value of the moment, which is MA, right? And this area is above the curve, so that's going to be plus. Area AB minus 1580 plus 160 over 8. So this is 160, width is 8. We get the moment value at B is equal to minus 300 inch-pounds or pound-inches. So I'm going to go from 1580 to something less negative or minus 300. This is 0 order, horizontal. That means this is going to be first order, straight line to there, right? Now we go to MC is equal to my old value, MB, right? This area is still above the curve, right? So it's going to be plus area BC. I'll just do this first here. So MC is equal to minus 300 plus 75 times 4. And that's going to equal to 0. 75 is this height, right? Times 4, I get 0. So I'm going to end up right there. I didn't write the shear value, so I'm going to say that VC is equal to VB, right? Minus 75. And that's equal to 75 minus 75 is equal to 0. So once again, 0 order, straight line, first order to there. And our highest moment value is right there, and that's easy because that's at where the beam is connected to the wall. It's easy to see that's where the most bending occurs. So if you're analyzing this beam, that's what you're going to put right there. Now this beam, I didn't tell you what kind of beam it could be. It's probably an I-beam or something like that. And that's the centroidal axis. This is my C value from the neutral axis to the outermost fiber. And then I, you know, from the previous material in the course, using the table and the centroid and all that, and you're able to calculate what the bending stress. This is going to be some number in terms of PSI, okay? One left.